All right, so our last talk before lunch, Zechuan Zhang, she was in Buffalo until this past June, and now she's in Trieste, and she will be talking about the inverse spectral theory for the periodic self-adjoint Zakharov-Shabat, and IST for defocusing NLS with periodic boundary conditions.
Thank you. The title is a little bit long. All right, so first I'll introduce the motivation for our present work. We all know that for the Nonlinear equation, the SD on the line can be formulated by the Riemann-Hilbert problem. And the SD with periodic boundary condition can be formulated by the finite-genus formalism. Sometimes we can use the algebraic geometric method to solve it. And the issue is the finite-genus formalism is very different from the SD on the line. So here comes the question. The question is there a way to solve the periodic problem in a way that is more similar to the SD on the line? Actually, we were inspired by McLaughlin and Belloch's work. They formulated the SD for the Hills equation with a Riemann-Hilbert approach and used it to solve the initial value problem for the KDO equation with periodic boundary condition. And here we generalize this approach to the Zakharov-Shabat problem and use it to solve the initial value problem for the Fox-Nonlinear equation with periodic boundary condition. All right, so first I'll give a quick review of the finite-genus formalism for periodic Fox-Nonlinear equation. So here is the famous Fox-Nonlinear equation with a Lax pair, and we always call the first half of the Lax pair the scattering problem, and it is also equivalent to an eigenvalue problem. And we call the operator. We call the operator L the Dirac operator and Z as the spectral parameter. And here I'll introduce the block-Flocky theory. So suppose we have a periodic boundary condition Q at x plus L equals Q at x. Here we choose L to be the period. Suppose we use Y to denote a fundamental matrix solution of the Zakharov-Shabat problem. We could show that Y at x plus L and Y at x are linearly independent, and they satisfy this relation. We call the matrix M the modular matrix. And the eigenvalues of M are the Floquet multipliers. We use rho to denote them, and rho are given by this equation. In this equation, there is a function delta. Delta is called the Floquet discriminant, and we can compute it. It is equal to the half of the trace of the monoidal matrix. We can also define the Floquet solutions. They're the solutions of the Zakharov-Shabat problem, which satisfy the eigenvalue problem. So block-Floquet theory tells us, suppose the modulus of rho equals 1 is equivalent as a bounded solution of Zakharov-Shabat problem exists. So in this way, we can write the Floquet multiplier rho as the exponent e to the I nu L, where we call mu the Floquet exponent. So here, if we go back to the Floquet discriminant, we could say from this equation, we could use quadratic formula to solve rho. So each delta corresponds to 2 rows, and each row corresponds to a block-Floquet solution. So for any given real Z, we have 3 different conditions from the discriminant. The first case is when delta squared is greater than 1. In this case, the blockade functions are bounded. The second case is when delta squared is less than 1. In this case, the eigenfunctions are bounded. And the last case is when delta equals 1, the blockade eigenfunction is periodic, and delta equals -1, the eigenfunction is antiperiodic. So if we focus on the defocusing equation, we could show that the Dirac operator is self-adjoint. So we can define the Lax spectrum sigma of L The Lax spectrum is the set of all the eigenvalues such that the bounded solutions exist. So if we look at these properties, the Lax spectrum sigma Q can also be written as all the set of the eigenvalues such that the discriminant is real and is between -1 and 1. So in the last few pages, I'll introduce some spectrums. So first is the Moon spectrum. From the definition, we could say that the Lax spectrum sigma of Q comprises a compound number of spectral bands separated by spectral gaps. So if we look at this figure, all the right intervals, this one, are the spectral bands, and between two spectral bands, there is a spectral gap. So here we can define the Moon spectrum. The Moon spectrum is a set we call it sigma j. They're the roots of delta squared minus 1 equals 0. It decomposes into two sets, the periodic eigenvalues and the antiperiodic eigenvalues. The periodic eigenvalues are the are the zeros of delta equals 1, corresponding to the periodic eigenfunctions, and the antiperiodic eigenvalues are the roots of delta equals -1, corresponding to the antiperiodic eigenvalues. We could show that all the periodic and antiperiodic eigenvalues are the edges of spectral bands. And the Moon spectrum can also be divided into two sides, the degenerate band edges and the non-degenerate band edges. The degenerate band edges are the double roots of delta squared minus 1 equals 0. So if we look at the figures, the degenerate band edges are some points like this one, and this two. They look like in the interior of a band. And the non-degenerate band edges are the single roots of delta squared minus 1 equals 0. So if we look at the figure, these are the non-degenerate band edges. So these are the information about the Moon spectrum. Actually, the knowledge of the Moon spectrum is not sufficient to reconstruct the potential. So in the next page, I'll introduce some auxiliary spectrums. First, if we use V to denote a vector solution of the Zakharov-Shabbat problem, and next note is the base point, we could define a Dirichlet boundary condition like this. And we can use this Dirichlet boundary condition to have the auxiliary spectrum 1 mu J's. Actually, this auxiliary spectrum was first introduced by Ablois and Ma. They also introduced another kind of auxiliary spectrum. The only difference is here where for the second component, they multiply the second component by I. There are some useful properties of the Dirichlet spectrum. The first one is all the Dirichlet eigenvalues are real. Each lies inside the spectral gap. The second one is there is exactly one Dirichlet eigenvalue of each type in each gap. And the Dirichlet eigenvalue in the open spectral gaps are called movable. They are dependent on X node, the base point. And all other Dirichlet eigenvalues are fixed. They are band edges and they are independent of X node. So finally, Ablois and Ma give the finite-genus reconstruction formula. So from these two formulas, we could say they only use EJs, mu J's, and eta J's. EJs are the non-degenerate band edges, mu J's and eta J's are the two auxiliary spectrums. So here we can do the Dirac spectral theory. And here after we choose the base point X node to be 0, and we use mu J to denote the Dirichlet eigenvalues. And also the sequence, the Moon spectrum zeta J extends to infinity in both directions. In particular, we have the asymptotic behavior of zeta J's and mu J's as J goes to infinity in both directions. And also we can define some integers J plus and J minus to describe the genus. So in this way, we can write the Lax spectrum as a disjoint union of combo intervals. And we can also define the spectral data associated to the potential Q. It comprises EJs. EJs are the non-degenerate band edges. Mu-Js are the Dirichlet eigenvalues, and sigma-Js. Sigma-Js are some indices, which I will introduce below. So in the next few pages, we'll show that as of Q, the spectral data is sufficient to uniquely reconstruct the potential. So here, if we go back to the Zakharov-Shabbat problem, we still use capital Y to denote the fundamental matrix solution. And if we recall the monodromy matrix, the monodromy matrix M is equal to capital Y at L. So the discriminant, the blockade discriminant is equal to half of the trace of Y at L. To set up a proper Riemann-Hilbert problem, unitary transformation is necessary. So here we define matrix U, and we multiply Y by U from the left and by U inverse from the right. So we can show that YTO defined in this way solves the modifies the Zakharov-Shabbat problem. And we define the Y tilde in this way so that the mu-Js, the Dirichlet eigenvalues, are the roots of the 1-2 entrance of Y tilde at L equals 0. Also, we can define the block for K eigenfunctions psi plus minus. They are the solutions of the Zakharov-Shabbat problem, which also satisfy these two conditions. We can also use these two conditions to explicitly write psi plus minus as a linear combination of Y tilde 1 and Y tilde 2, where Y tilde 1, 2 are the first and second columns of Y tilde. Also, we can define the indices sigma k. So sigma k equals plus minus 1 if Y tilde 2 at mu k is associated with the blocking multiplier rho plus minus. Sigma k equals 0 if mu k coincides with one of the band edges. And we can also define a matrix block case function in the lower and in the upper and lower half planes. So from the definition from the expression of phi plus minus of psi plus minus, we could say there is a denominator Y tilde 1, 2 at L. And we know that the Dirichlet eigenvalues are the roots of this component. So here we could show capital psi has poles on the Dirichlet spectrum, and it is discontinuous on the real axis. We can also compute the asymptotic behaviors of Y tilde, and psi as they go to infinity. The result is capital psi has a nice asymptotics as it goes to infinity, which allows us to use it to set up a Riemann-Hilbert problem. Okay, now we're ready to do the inverse spectral theory. So first I'll introduce some auxiliary functions, F node, F plus, and F minus. There are some finite or infinite products with different indices, sigma j's. And we can also use these functions to define 2x2 matrix value function B, capital B. We use capital B, we define capital B in this way for two reasons. The first reason is we want to use this diagonal matrix to cancel the poles of the Riemann-Hilbert problem. The second reason is we want to use this coefficient to make sure that the determinant of the Riemann-Hilbert problem is always equal to 1, so that we can get the uniqueness of the solutions. So BJ defined in this way, BZ defined in this way is completely determined by the spectral data S of Q. All right, so here we are ready to set up a Riemann-Hilbert problem. We define a sectionary meromorphic 2x2 matrix phi in this way. Psi is a matrix block-Floquet solution, capital B, and e to the izx sigma 3. And also we define a counting function M. A counting function M is to describe the square root, the jump of the square root. And also we can give the jump matrix along the gaps and the bands. So here we have the Riemann-Hilbert problem. Define a 2x2 matrix, matrix value function phi such that phi is a holomorphic function for z in C minus R. Phi plus minus are continuous functions for z R minus ek and have at worst potential singularities at ek's, thanks to the definition of B. And also the jump relation, the asymptotic condition, and the boundness. So the next step is to show that the solution to the Riemann-Hilbert problem is unique. So first we show that if phi is of the Riemann-Hilbert problem, then the determinant is always equal to 1. And we use this result to show that the solution of the above Riemann-Hilbert problem is unique. Once the solution of the Riemann-Hilbert problem is unique, we could use it to reconstruct the potential matrix Q. The next step is about the time evolution. So first we notice that the blockade discriminant delta and zetas are the main spectral, are time independent, but the Dirichlet values mu j's are time dependent. So here we can use the next equation to derive to ODEs. This one. There the ODEs for the time-dependent Dirichlet values and time-dependent blockade solutions. In the second ODE, we could find there is a function alpha plus minus. It is a function of t and z only. The alpha plus minus are very complicated, but the asymptotics as it goes to infinity are very simple. So here we can use alpha plus minus to define a new function e plus minus. If we multiply the blockade solution by e plus minus, then we could.
Sorry, but your alpha plus minus, they seem to depend on boundary data, QX and.
Yes, but then QX and 0.
Okay.
Yeah, so we define the time-dependent blockade solution, psi check plus minus. We could show that psi check plus minus satisfy the modified Lax pair, which tells us really psi plus minus are the time-dependent blockade solution. We can also define the time-dependent jump matrix. We call it V check. The time-dependent matrix value blockade solution, we call it capital psi check. And finally, we define phi check. Phi check is defined similar as phi, but here everything is time-dependent. Also, we can use all these functions to set up a Riemann-Hilbert problem, a time-dependent Riemann-Hilbert problem. And we could show that the solution to the Riemann-Hilbert problem is unique, and we can use the solution to recover the potential matrix Q. Here are some additional results, but the details are omitted here. The first one is we also have the relation with matrix Baker-Kaiser function and the theta function representation of the solutions of the Riemann-Hilbert of the analysis equation. And we also have the formulation of the RHPs to ensure periodicity of the solution in time and space. Also, what is more important is using the second set of Dirichlet values would work as well. There are some final remarks. The most crucial one is there must be a bijectivity between the two sets of the Dirichlet values. Thank you, that's all.
Questions?
So, but this, sorry, this bijection between the Dirichlet eigenvalues does it take maybe some, I don't know, more transparent meaning if you look at the embedding in the Jacobian of the curve?
Oh, okay.
I don't know, I'm asking, it's not a
We are
statement.
not sure. We just get there must be a bijectivity, but we don't know what it is. It
Okay.
is what we're going to figure out.
Well,
So if you have a finite gap potential, right, things simplify.
Mhm.
Can you relate, like using this approach, can you get some information about how the gap constant that you would write down for a finite gap Riemann-Hilbert problem relate to yours? In terms of Dirichlet eigenvalues or something?
I think we can, but we didn't do it.
Okay.
Okay. If there are no more questions, then let's thank.